Now let's talk about a different type of probability problem we need to work with, conditional probabilities. Now, here's the idea of conditional probabilities. Let's draw two cards from a deck of cards. All right, we're going to first draw one card, and then we'll replace that first card before we draw a second card. What is the probability of one of those two cards being a queen and the other one being a jack? Now, if this were just one card, remember those would be mutually exclusive events. But since we have two cards, it is possible to draw two cards, one of which is a queen, the other is a jack. It is possible. So, what's the probability of drawing a queen? It's 4 out of 52. There are 4 queens in a deck of 52 cards. You put the queen back. Now, what's the probability of drawing a jack? Well, you pull out a card. There are 4 jacks out of a deck of 52. Okay, not a problem there. Now, this time, let's draw 2 cards. We take one card out, we leave it out, and then draw a second card after that. Now, what's the probability of drawing a queen and a jack? Again, it's 2 cards, it's still possible. Probability of drawing a queen is 4 out of 52. But now that we've kept one card out, we only have 51 cards left in the deck. So the probability of drawing a jack is now 4 out of 51. The probability changed because of the first card that we drew. All right? This is the concept behind a conditional probability. When one event depends on what happens with another event, that's a conditional probability, and we draw it this way. The probability of event B happening given that A has already happened. This line in the middle means given that. In other words, with the condition of event A. What is the probability of B happening given that A has already happened? So in our first card example, the probability of drawing a jack is 4 out of 52. But the probability of drawing a jack, given that we've already drawn a queen, is 4 out of 51 because that queen is now out of the deck. It changes the number of cards in the deck. All right, let's look at this from another point of view. Let me introduce you to another tool called the confusion matrix. Why it's called the confusion matrix, I honestly have no idea, but it should be the anti-confusion matrix because it helps sort things out. The idea of a confusion matrix is that it organizes the probabilities and relative frequencies when you're dealing with 2 events at the same time. And the way it works is you have one probability or one category, A, and we'll make that a column in our table. And then not A, the complement of A, will be another column. Then we go to our second event. Event B will be a row in our matrix or in our table, and its complement, not B, will be another row. And then where they meet, we're talking about people that are in that particular column and that particular row. So this column here, we're talking about probability of being both in A and in B. Down here, we're talking about the probability of being in A, but not in B. And here would be not A, but yes, B. And this would be not A and not B, not being in either group. Okay. Generally, we use this for probabilities. Often the confusion matrix is also used to count. In other words, we'll have just the number of events that are the number of people in those 2 categories. The number of people in both A and B, the number of people not in A but in B, and so on. Okay, that's the idea of confusion matrices. Let me do this with an example. Let's do this with the questions, who likes football, who likes basketball, and who likes both? You gather all that data, and you put it together in a table, and you find there are 82 people who like both football and basketball. But there are 56 people who like football but do not like basketball. 62 people who do not like football but do like basketball, and 25 people that don't like either sport. Okay, there is just the count of each category. But we could turn this into a probability, or probably a better term would be the relative frequency of each category. How do we do that? We take the total number of people. If we add up all four groups, we'll find that we have a total of 225 people. So we turn each of these numbers into a fraction. 82 out of the 225 people we sampled like both sports. That comes out to 0.36 or 36%. And we do that for each of the four different combined categories. And you've got yourself a relative frequency confusion matrix. Good? All right. Let's use this to talk about conditional probability. Remember our conditional probability, I'll go back here, where event B depends on what happened with event A. Probability of B given that A has happened. All right. If I randomly choose a student, what are the chances that they like both football and basketball? Well, you look for the one cell in this table that is both football and basketball. Okay, 82 out of 225 people like both football and basketball. That's 36%. Nice. Now, slightly different problem. If I randomly choose a student, what are the chances that they like football? I apologize. This word can be scratched out. That shouldn't be there. What are the chances that they like football if we already know that they like basketball? Think about that, how that's different. Before, it was what's the probability that they like football and basketball? Now we say, well, we know they like basketball. We know that already. Now what are the chances that they like football? Well, if we already know that they like basketball, that means that we know that they have to be in one of these two groups. And of these two groups, we are hoping to find someone who likes football in that group. Okay, so now we're going to calculate a probability just with these two cells here. Okay, that's the idea of the conditional probability. You're restricting yourself to a smaller starting point, a smaller subgroup, and then you're finding the probability out of that smaller subgroup. So if we take the 82 people that like both football and basketball, and the 62 who like basketball but don't like football, that totals 144. Out of those 144 people that do like basketball, 82 of them also like football. That's 59.64%. Nice. Okay. Out of all the people who like basketball, 144 of them, 82 of them also like football. Okay. Now, we just put it up the counts. We didn't actually deal with probabilities. Let's put in probabilities. Put in what's actually in these cells. You have 82 out of the 225 people are like they like both football and basketball. But 144 people out of the total of 225 like basketball. Okay, and that simplifies to what we got earlier. Well, this 82 out of 225, that is just the probability of football and basketball. And this number down here, 144 out of 225, that is the number of people who like basketball. That is both of these cells added together. So that's just the probability of liking basketball. And right here, we just derived the equation for conditional probability. When one event depends on what happens with another event, we deal with conditional probability, and we can find the probability of B given that A has already happened by finding what's the probability of A and B divided by the probability of A.